Hello, welcome to this video about our Teledyne EV10AS940 ADC. The EV10AS940 ADC is the most advanced microwave capable ADC with large input bandwidth up to 35 GHz, a single-ended analog and clock inputs including digital features. The EV10AS940 offers digital down conversion capabilities to select specific frequency band of interest from the data captured and optimizes the amount of data to transfer to the FPGA. When the DDC is enabled, several features and configurations are available. In this video, we will focus on two main digital features of this ADC, the frequency hopping and the beamforming. This ADC has the capability to quickly switch the NCO frequency, and thus the frequency band of interest is supported, up to 4 digital channels. Let's start by describing the bench that will allow us to explain and demonstrate this frequency hopping feature. We have here our Teledyne AS940 FMC evaluation board, a mezzanine FMC Plus board connecting to our Teledyne FPGA carrier board with an AMD Kintex UltraScale KU35 FPGA. Around these boards we have 3 signal generators. For clocking, we have a 20 GHz signal generator. For the analog input, a 40 GHz signal generator and a 6 GHz signal generator with another. And we have a PC with our GUI developed for ADC evaluation purpose. The powering up of the bench is not part of this tutorial and was explained in a previous video. You will find the link for the video below. After powering up, launch the GUI. Click on the connect icon to connect the board. Check that the socket icon turns green. This indicates that the AS940 board is detected. Click on the DUT button. Ensure that the IDs correspond to expected values indicated in the user guide. Then enter the F-clock frequency. For this tutorial is 12.8 GHz. The GUI can be used to calculate the coherent frequency for each F-in. We will pass through the coherent frequency settings that are explained in a previous video. So we will use here the coherent frequencies calculated for F-in 1 equal 3.1 GHz and F-in 2 equal 33.1 GHz. Then, to have an all-in-one configuration, press the init sequence button. This will perform a reset, clock synchronization and load optimal settings in the AS940 at once. This also activates the background calibration of the ADC. Now we will see how to configure the ADC to perform frequency hopping. First, click on the DDC button. It will open a window with 3 tabs: NCOPA settings, FFH and beamforming. In the NCOPA settings tab, at the top of this tab, you can activate the DDC channels, choosing between 1 coarse channel or from 1 to 4 fine channels. You can also choose the decimation ratio. Under this, there is a table that allows you to choose between 8 sets of parameters, frequency and phase, here represented by the columns, and the channels NCOs are represented by the lines. In this video, we will activate 1 fine channel with a decimation ratio of 32, and we will use 3 of the 8 sets of parameters available for the fine channel used. In the channel 0 line, put in the first column 5 3.3 gigahertz. In the second column, put 3.1 gigahertz, and in the third one, put 2 gigahertz. Now, click on FFH tab. The fast frequency hopping uses 3 GPIOs. These GPIOs allow the selection of parameter sets. By default, these GPIOs are deactivated. You need to activate the GPIO clock and choose a frequency for this clock. Then click on I/O enable. You can choose the phase mode. You have the reset phase mode. When hopping to another NCO frequency, the phase is reset to its initial value. The continuous mode, the waveform has no discontinuity when changing its frequency. And you have the coherent mode. When hopping back to the initial NCO frequency, the initial phase is conserved. Phase accumulator always running in the background. Here we will keep the default value, reset continuous mode. Below, there is a table that allows selecting which configuration, which parameter sets you want to hop to for each channel. On the right, next to this table, you can see a graphical representation of the signals sent to the FFH GPIOs of the ADC. For this video, we start by keeping the default setting, the config 0 for the channel 0. Once the GPIO config is chosen, click on Start button. On the right, you will see the parameter sets in use for each channel. These fields can also be modified. To see the selected configuration on the first Nyquist, click on Spectrum Overview tab. If nothing displayed on the graph, select the number of samples and click on Refresh button. You will see color rectangles. These rectangles represent the selected NCO frequency. You can move them by selecting the dashed line. This will change the NCO frequency. Click on IQ Display and Acquisition to view the acquisition made by the ADC. This tab allows you to start data acquisition. There are 3 buttons on the left. First button to make one acquisition. A second button play to make a continuous acquisition. And a third button to stop the continuous acquisition. On the right, we can see the data in time-based format or FFT format. Below, there is a table that shows the perfs on the IQ plot. Start the acquisition by clicking on Start button. We can see the FFT of the digital channel 0 for the parameters set 0, first column of the parameter table. To illustrate the frequency hopping, we will just change the selected config to jump to a different parameter sets of the NCO. So you must go to the I/O commands of the FFH tab. In the GPIO table, select a different configuration for channel 0, 0 to 1, then click on Start. We see that the settings in use changed. If you go to the Spectrum Overview tab, you will see that the rectangle has moved to the first peak, meaning that the NCO frequency associated to this channel has changed. You can check the FFT of the digital channel 0 for this NCO configuration on the IQ display and acquisition window. To hop to the third NCO frequency for the channel 0, repeat the same step as before. So go back to the IO commands of the FFH tab. In the GPIO table, select another configuration for channel 0 from 1 to 2, then click on Start. Go to the Spectrum Overview tab. You can see that the rectangle have moved to an area with no signal. You can check the FFT of the digital channel 0 for this NCO configuration on the IQ display and acquisition window. In this first part, we have seen frequency hopping capabilities of the EV10AS940 ADC thanks to embedded NCOs. Even not demonstrated here, the frequency hopping is deterministic when using GPIOs of the ADC. In the second part of this video, we will see beamforming capabilities of this ADC. So, in addition to NCOs, the EV10AS940 has the capability to set gain, integer delay and fractional delay independently on each DC channel enabled to facilitate deterministic timing, multi-chip synchronization and digital beamforming. For beamforming, we use only one data generator. Clock configuration here is the same as for the frequency hopping. The clock is set up, now we will focus on the beamforming configuration. To do so, click on the DDC button. Then click on Activate 4 channels. Now we want to set the NCO frequency for the 4 channels we have activated. In our case, we will use the first set of parameters, the default one. Here, to set the NCO frequency, we will select the NCO value in the box at the bottom and then click on Set All To button. The FIN selected is 23.1 GHz. The NCO frequency chosen allows to easily visualize the delay on the IQ plot. Another way to set the parameters is to do it value by value in the first column of the table. Click on Sync button to synchronize the phase of all channels. At this stage, we have only set the NCOs. Now we will focus on the beamforming tab to set the gain and delay on our 4 channels. Click on Beamforming tab. You can select the gain of each channel using cursors on the right of this tab. On the left, you select the delay. There are 2 types of delay. The first one is the integer delay. It allows you to add a delay of 1 clock per step. The second delay is the fractional delay. It allows you to add a delay from minus 0.5 to plus 0.5 times a clock period. At the bottom, there is a tool that allows you to select a delay and it gives you the fractional delay and integer delay to set. It also gives you the associated angle of the selected delay. Click on IQ Display button. Everything is set up. We can start the data acquisition. Click on Play to start the measurement with default parameters. No delay on the gain of 1. We can see that all the channels are the same. We can click on channel buttons to activate, deactivate the display of each channel. Then we can modify the delays and gain to see the effect on IQ plot. First, we can modify the gain of one channel and see the effect. The amplitude in the IQ plot have changed. Then we can modify a fractional delay and see the effect. The phase between the channel modified and the others have changed. In the second part, we have seen beamforming capabilities of the EV10AS940 ADC by configuring gain and delay setting for each digital channel independently. This capability of beamforming is demonstrated here with one ADC. Obviously, this capability makes even more sense in multi-chip applications. We have reached the end of this video. We went through the frequency hopping and beamforming features of the EV10AS940 ADC. The AS940 evaluation board seen in this video is available, so you can start evaluate and test this ADC and its digital features right away. If you have questions or if you are interested on the EV10AS940, please contact us using Teledyne E2V hotline email address.